Our solar system, the place we call home, lies about 26,000 light-years from the center of our galaxy, the Milky Way. Or around 2/3 the way out. The story of how these huge planets, average yellow star, is 6 billion years long. And since we don't have that much time, I'll speed it up a bit. It starts with a bang. Long ago, an ancient star exploded, littering space with swirling clouds of the materials it had made while it lived, and the heavier metals it created as it died. We know this because we can see similar fields of dust out in space. They are called nebulae, and they are very beautiful. Every nebula is different, and in our case, the clouds contained nitrogen and oxygen and iron and silica and all the other stuff needed to build a world like ours. Then the tireless force of gravity started to pull it all back together. And the heavy engineering that produces planets began. Spirals of dust began to form. And at the center of one of these, a rocky planet called Earth started to take shape. Built of stardust and assembled by gravity. Fast forward 100 million years, and it had grown into a giant ball, sweeping up billions of tons of celestial debris. This is where the Earth came, and therefore how you and I began. But our planet would have remained a large, sterile ball of rock and metals and minerals forever, were it not for one more event, one forces of nature. 93 million miles away, at the heart of the giant nebula, the pressure and temperature of a ball of hydrogen gas had become so great that the atoms were beginning to fuse. New star, our sun, was coming to life. As the sun ignited, it gave off a huge blast of solar wind, radioactive gust of energy. This blew all the remaining dust and gas that was left over from the nebula out to the edge of the solar system, which is why everything is nice and orderly today. In the outer reaches of the solar system, we have the huge gas planets, Jupiter, Saturn, Uranus, and Neptune. Further in are the denser, rockier planets, Mercury, Venus, and of course, the Earth. Lucky for us, the Sun is 865,000 miles in diameter, or just the right size to burn consistently for a very long time. 8 billion years. Long enough to take place. Life.
If we could open up the sun, we'd see layers of dense hydrogen gas, hundreds of thousands of miles deep. And at its center, the core, the sun gives birth to light. Forged in one of the most violent reactions in the universe, nuclear fusion.
The specific nuclear reaction that powers the sun is fusion. Fusion of hydrogen into helium. You take two hydrogen atoms, you ram them together, and what's left over is a helium atom.
It sounds simple enough, but it's not.
It's actually hard to get two atoms to fuse. Two protons have the same charge, they're both positively charged, they want to repel each other.
Protons don't like to get close together. They have to come together with a huge amount of energy or velocity to get close enough to begin to fuse, and that's very, very rare.
To force protons together takes immense amounts of heat and pressure, generated by the invisible hand of gravity. The sun contains 99.8% of all the matter in the solar system. That's a lot of mass. All that mass pulls the sun together with unimaginable gravitational force.
But with gravity crushing things down, things get close enough together and nuclear fusion happens.
In this nuclear compactor, hydrogen atoms slam together 100 million quadrillion times each second. Some of these collisions are so powerful that atoms fuse, releasing energy.
When the protons come together, to bind together, they lose a little bit of mass, and that mass gets converted into energy. And every second of every day, about 5 million tons of stuff is being converted to energy. It's amazing.
A nuclear reactor works by splitting up large atoms such as uranium. This is known as nuclear fission. These large atoms are very unstable and can be split up by firing a neutron at them. They split into smaller atoms and a number of neutrons. If we measure the mass of the initial atom and the total mass of the products after the split, there seems to be a discrepancy. Some mass seems to be lost. Einstein's famous equation, E equals mc squared, shows that this incredibly small amount of lost mass is converted into a huge amount of heat energy. So we know each atom splitting up gives off some heat energy. But it gets really exciting when you put a bunch of these atoms together. As one atom splits up, it releases some energetic neutrons ready to split up some more atoms, which in turn releases more energetic neutrons, which will split up some more atoms, and on and on. This is known as a chain reaction. The problem is, if we don't control this reaction, we soon end up with an incredible amount of heat energy, which is impossible to control, resulting in what is known as a nuclear meltdown, which isn't very useful when trying to run a power station. To control the rate of reaction, we need a substance which can absorb the neutrons, stopping them from splitting up other atoms. In a nuclear reactor, this is done by control rods. When lowered, these control rods stop the reaction if necessary. They are built and positioned in a way that ensures they drop into the fuel in the case of an emergency such as a power cut. During normal operation, they are raised and lowered accordingly to vary power output. The lower they are, the lower the rate of reaction, which means a smaller power output. The higher they are, the higher the rate of reaction, which means a greater power output. With the aid of the control rods and other design features, nuclear reactions can be regulated, meaning there is a constant production of manageable heat energy, which then can be used to heat water into pressurized steam. This is then used to turn turbines connected to a generator, producing large amounts of electrical energy. Nuclear reactions can release a lot of energy, which can be very dangerous, but because of the ever-growing hunger for energy, scientists are working very, very hard to make this technology safer and potentially reducing the use of fossil fuels.
A speck of uranium, the size of the dot over an I, would contain more than 2 million trillion atoms. The heart of the atom is the nucleus, 20,000 times smaller than the atom itself.
This tiny nucleus at the center of the atom is made of protons and neutrons, and they're tightly bound together. Unlike billiard balls, protons and neutrons can't be knocked around. They remain fixed, unchanging, inside the nucleus. And it's actually the number of protons inside each nucleus that defines the element. An atom with one proton as its nucleus is the element hydrogen. In the atomic world, it doesn't get any simpler. Every atom in the universe with one proton is hydrogen. An atom with two protons is the element helium. Now you'll notice this one also has two neutrons, represented by white balls. Now some helium atoms have one neutron, some have three, but all helium atoms have precisely two protons. An atom with 6 protons is the element carbon. It could be the carbon in a tree or the carbon in diamond. All have exactly 6 protons. Each different element has a unique number of protons. 7 is nitrogen. 8, oxygen. 79 is gold. But have a look at this. The uranium nucleus has a whopping 92 protons and usually 146 neutrons. It is the biggest nucleus on Earth. So big that it is groaning under the strain. And Ernest Rutherford and Frederick Soddy find that it is doing something extraordinary. It actually spits out chunks of itself. And these chunks are radiation. Now, they contain protons, so when uranium releases radiation, it's losing protons. So it no longer has 92, and that means it's no longer uranium. It's a completely different element. Ernest Rutherford and Frederick Soddy are witnessing the uranium nucleus transforming itself. And this challenges our fundamental understanding of the physical world. A nucleus doesn't just change. So this suggests the dark and magical arts of the alchemists.
Element. So, is radioactivity useful or just dangerous? Wherever you are sitting, it is quite likely that there is a device nearby which contains a source of alpha particles, a smoke detector. The source is radioactive americium. You are totally safe from these alpha particles, which cannot travel more than a few centimeters in air. Beta particles penetrate much further through materials than alpha can. Radioactive atoms are used in medicine as tracers, to show where chemicals travel in the patient. Beta particles are emitted and have enough energy to emerge from the body and be detected. There is a third type of nuclear radiation, gamma, which is not a particle at all. It is an electromagnetic wave, like microwaves or light, but it is actually 1,000 times more energetic than visible light. Gamma rays may pass right through your body. Gamma is used to zap the bacteria in fruit to increase its shelf life, or in radiotherapy to kill cancer cells. Radioactive substances get hot, and this heat can be used to generate power. This heat has been put to use in space probes and, in the past, in pacemakers for hearts. The more abruptly nuclear radiation is slowed down, the more damage it does to the atoms it hits. This is called ionization. alpha causes the most ionization as it crashes into other atoms, and gamma the least. For humans, the most serious effect of radiation is the damage that it can cause to our DNA. Although alpha cannot penetrate your skin, if you inhale or ingest a radioactive nucleus, the health consequences can be severe. Radioactivity is both useful and deadly.
I'm about to go into the hospital at Pripyat. And this is where the firemen were taken after they fought the fires at the Chernobyl reactor. That is the door to the emergency room at the Pripyat hospital. This is where the firemen were brought after fighting the blaze over at the Chernobyl reactor. Their clothing is actually still in the basement. But I want to go down there to see how contaminated that clothing is. And I want to understand what those firemen went through.
BioNerd says the radiation down there might be 10,000 times higher than natural background. And that's dangerous, so we need protection. You don't want to ingest or breathe in this stuff. I think this is the time when I get a real sense of the danger of radiation. It's right here. The main radiation down here is from one particular fragment of split uranium atoms. It's called cesium-137. And the radiation it's releasing is what you can hear.
It's hot. It's hot here. It's really hot.
On the floor up ahead, what we had come to see, a boot from one of the Chernobyl firemen.
What do you got on that boot?
2 millisievert per hour.
2 millisieverts an hour?
Yeah.
It's overloaded.
That's 10,000 times natural background radiation. And then we found a room with a pile of the firemen's gear. Tunics, boots, and helmets heaped on the floor.
But the readings are so high.
Right outside the door, I'm getting half a millisievert an hour. That's 500 microsieverts an hour just outside the door.
That's 2,500 times higher than natural background radiation. And I was happy to stay outside. But then BioNerd went in.
Now the tube is actually overloaded.
Alright, I think we need to get out of here. Let's go.
Yeah.
The history of life on Earth is a mystery that biologists and geologists have been trying to unravel for hundreds of years. The most important clues to this mystery are fossils. In order to understand how organisms evolved through time, we have to know when their fossils formed. Fossils form when organisms are buried in sand and mud. As layers of deposits build up, older sediments are compressed into rock. The organisms form fossils within the rock. The younger the rock, the higher it is in the rock layers. The fossils within the rock layer are the same age as the rock itself. In studying the Earth, scientists discovered that similar fossils appeared in a consistent way through the layers or strata of rock in different locations around the world. These fossils acted as an index to the time the sediments of the rock were deposited. Comparisons could be made between buried rocks based on the fossils within it. In this way, scientists were able to develop a geological timescale. Important events in the history of life, like mass extinctions, were apparent from the disappearance of fossils at a consistent layer in rocks around the world. With a relative timescale, biologists knew the order in which fossil organisms appeared, but no one could be sure about the precise ages of the fossils. Calculating the absolute ages of fossils wasn't possible until radioactivity was understood. The gradual breakdown of a radioactive substance in rocks is the clock that scientists use to measure geological time. In the process of emitting radiation, radioactive isotopes decay into different isotopes, eventually producing elements that aren't radioactive. For example, the radioactive isotope uranium-238 decays into the stable isotope lead-206. Each radioactive isotope decays at a unique constant rate, described by its half-life. The half-life is the time it takes for half of a given quantity of a radioactive isotope to decay into another isotope. The half-life of uranium-238 is 4.5 billion years. That means it takes 4.5 billion years for half of a sample of this isotope to decay away. Consider a rock containing uranium-238 that formed at the time of the earliest known fossils, about 3.5 billion years ago. Today, it would contain 58% of the original quantity of uranium-238. An isotope with a shorter half-life would be better for calculating the age of a younger rock. It takes millions of years for a significant amount of uranium-238 to decay from its starting level. An isotope with a shorter half-life would decay more significantly in a shorter time. The greater change in the amount of isotope would allow a more accurate measurement of the age of a younger rock. Radiometric dating is the method of determining the ages of rocks and fossils using radioactive isotopes. Using sensitive equipment and great care, scientists measure the amounts of a radioactive isotope and its decay products in a sample of rock or fossil in order to calculate its age. With the help of radiometric dating, the relative ages of rock strata and their fossils have been converted to absolute ages, and our picture of the history of organisms evolving on Earth has become increasingly clear and consistent.